All right, chapter 14 is about complex integration. These are the 4 sections of 14. The first one is line integrals and definition of line integrals in complex plane. Then we talk about Cauchy's integral theorem that says, in fact, that integral over a closed path is for a analytic function is 0. And then we have Cauchy's integral formula that gives you the basically the integral, or in terms of the value of the function at one point when it is a singularity, when at some point. And then we have extension of that has some more formulas that are related to derivatives of functions, and we use those derivatives to evaluate integrals. So this is a very important chapter, and then later on in chapter 15 and 16 we see that how it turns into a very powerful method. All right, so let's get started. The integral, definite integral of the dz is denoted by this symbol. As you see, it's integral over curve C. In here, we specify what curve we integrate over, because it's not just the matter of from one point to another point. It is how you go from one point to the other point. And then this C, curve C, can be parameterized like this. And then this curve should be smooth so that this derivative with respect to the parameter exists. And then how do we define the integral? What do we mean by an integral? Remember, in real calculus, when we wanted to define integral from a to b fx dx, what we did was we looked at the graph of the function from a to b, and then we divided this interval between a and b into n divisions, and then evaluated the function at some point in that division, maybe in middle point or any other point, doesn't matter. For example, this figure is for evaluation of the function at this middle point, and then multiply by this width of this section. And then you get the rectangle like this. And then the second one, you get another rectangle, another rectangle, another rectangle. And we add all of these rectangles. You see f of xi delta x. This is the area of each rectangle. You add them all up, and then you take the limit of this quantity when n goes to infinity. It means the number of partitions goes to infinity. We use exactly the same methodology to define complex integrals. This is a curve C over which we want to do the integral from z0 to zn. Again, we divide it into many pieces. The way we divide that is by using the parameterization of the curve. And parameter we use is t. So this curve is parameterized with t, and when t is a, it gives us this point, z0. If t is b, it gives us this point. So we divide the interval of t into n divisions, and for each one of t1, t2, tn, we have the parameterization. It gives us zm equal to z of tm, for m equal from 0 to n. All right, so in fact we do divide t interval into n pieces, and that gives us n points, or n plus 1 points if you wish, along the path. And then so this divides the path into n pieces, and then for each piece of the graph we choose 1 point, which is like this parameterization, the curve evaluated at some number t between tm minus 1 and tm, which gives us zm minus 1 and zm. And that number between tn minus 1 and tm is a t value that gives us a number on the curve, right? And then for this interval, we also have a absolute value of Zm minus Zm minus 1, which is the length of this line, right? From here to here. And then we divide the value of the function at Zn, zeta m, multiplied by this length. So this is what we have here. And we add all these pieces together and we call it Sn. And then we take the limit of Sn as n goes to infinity. And as delta Zm go to 0 for each one of the intervals. So these, we don't keep any of the intervals finite. So all of them go to 0. And so this limit is called the integral of fz dz. If this should be if the curve C is a closed curve, we denote the integral by a circle on it to show that the integral is on a closed path C. So if C is closed, we put a circle on the integral that indicates that it is a closed path. All right. So this is basically very similar to the definite integral definition in real calculus. We do the same thing. But of course, we are not going to do this procedure, as you know, in real calculus. We are not doing this. This is called Riemann sum. We are not calculating Riemann sum for every integral, but we have methods to evaluate the integral without going through all of these shenanigans. All right. We said that it has this integral, the way we define it, because it's a summation, it has these properties. It's linear, and because integral of k1 f1 plus k2 f2 becomes k1 integral of f1 plus k2 integral of f2. And sense reversal is the same as real integral. If you integrate from z1 to z2 of z dz, it is negative of integrating z2 to z1 f z dz over the same curve, going backwards. And partitioning also, if curve C can be divided into C1 and C2, the integral over curve C of f z dz is equal to integral over the C1 part plus integral over C2 part. So this is called partitioning of path. So you can break the integral into different pieces. And then we said that there's a first evaluation method similar to what we had in a real calculus, which we call fundamental theorem of calculus. Integral from a to b of x dx can be evaluated if you find a function whose derivative is this fx, means this capital F derivative is f of x, and then the integral is the capital F evaluated at b minus capital F evaluated at a. That's why we do the antiderivative and then evaluate at upper limit, lower limit, and subtract. This is a fundamental theorem of calculus. We have similar thing for complex integrals, but it is only useful for analytic functions. So if fz is analytic in a simply connected domain D, then there exists an indefinite integral of fz in D. This means that there exists an analytic function f capital F of z such that f prime of z is equal to fz in D. And for all paths in D joining the 2 points z1 and z2, in D we have integral from z1 to z2 fz dz equal to f evaluated as z2 minus f evaluated as z1. And this is path independent, right? It doesn't matter where, how you go from z1 to z2. If fz is analytic, it doesn't matter. We will see why. All right, so this is very similar to fundamental theorem of calculus, but the only thing is that the problem is that it is only good for analytic functions. All right, so let's try some of these examples. I want you to calculate this. What is the integral from 0 to I plus 1 z squared dz? Can you calculate that? Let me give you the pose, and then you can answer which one you came up with. Of course, it takes a little bit to do that. What do you think the answer is? So you know that you do the antiderivative, which is very similar to what we had in real calculus, and then you put the upper limit minus lower limit. It is basically mostly arithmetic at this point, complex arithmetic. Right, the half of you answered already. All right, I guess that's enough time if you want to answer. So let me share the result. So these are the results. You see there's one person who said A, and more people said D and B, and some people said C. Does anyone want to share why they answered their answer?
I got the answer C over there. So the integral become the ZQ2 over 3, and the GQ become I plus 1Q, and it become IQ plus 1 minus 3 plus 3I. So it's become -2 plus 2I over 3. So C is the answer.
C is there. Okay. Anybody else? I saw the bars on B and D went up very fast. So those people decided too fast, and those are wrong numbers. They're not wrong answers. The C is the correct answer as he described. Thank you for that. So if you want to answer, this is the result: 1/3 of Z cubed, and then you evaluate it at 1 plus I. So it becomes 1/3 of 1 plus I cubed. And 1 plus I, let me explain a little bit more. 1 plus I has a module of a square root of 2. You see, it is right here. 1 plus I is here, right? It has a module of a square root of 2, and it has a 45-degree angle, or pi over 4. If you square it, it comes here. If you cube it, the angle becomes triple. It comes in this direction, and the module is 2 square root of 2, becomes square root of 2 cubed, right? So it becomes 2 square root of 2, So you can write this. See the y is actually 2, the x is also -2. So that's -2 plus 2i. So you should be just thinking about which one of these, but of course this one has a module of the square root of 2/3. This has module of 2 square root of 2/3, and then you see that the correct answer is C. Okay. So be careful when you're answering question. It is enough. You have enough information to get to the right result. So be careful. Let's try another one. Integral from -i pi to I pi, cosine of z dz. What do you think the answer to this one is? All right, I think can stop it now. So this is the results. Does anybody want to share their opinion?
I think the integral become the sine, and sine I pi become I sine of pi. So and then we have a negative sign of that. So we have 2i sine hyperbolic of pi.
All right, so you answered A?
Yes.
Yeah, all right. Yes. So becomes sine of z, and from I pi to -I pi, so becomes 2 sine of I pi. And sine of I pi, as you remember, is 2i sine hyperbolic of pi. And the answer is A then. That's correct. Very good. 23.0975 I. Any questions?
Yeah. How did the negative I pi
Negative I pi. So sine of we have sine of I pi minus sine of negative I pi, right? And sine function, the same as in real function, sine is an odd function. So sine of negative I pi becomes negative sine of I pi. With this negative becomes positive. So it becomes sine I pi plus sine I pi. So it becomes 2.
Okay.
So this is odd function. because you see sine of any z is equal to 1 over 2i e to the iz minus e to the negative iz. So if you put z, if you change z to negative z, you get a negative sign. So the sine of negative z is equal to negative sine of z. Right? Because
Okay.
this becomes this one and that becomes this one. So we get a negative sign. Right? So it's an odd function, the same as all the properties of sine and cosine actually transfer into z, into complex numbers. All right. All right. So the answer is A. What about this one? All right, we have 50% of the answers in. All right. I'm going to end it in about a few seconds. Please answer faster. All right. So let me end that. All right. So most of you answered B. And some said A or C or D. Who wants to share?
I think the answer should be C because when we integral, it becomes 2e to the power z over 2.
Mhm.
When we substitute the number in, The a plus 3 pi I and the a minus pi I is actually the same number, and so it becomes 0.
Oh, okay. Very good. Yes, the answer is C. All right, let's look. Becomes 2e to the z over 2, and then you have to put 8 plus 3 pi I for z, and 8 minus 3 pi I and subtract. So it becomes 2 times 4 plus 3 pi I over 2 minus 2 e to the 4 minus pi I over 2. So 2 e to the 4 can be factored, and then you have e to the 3 pi I over 2 minus e to the negative pi I over 2. So 3 pi I over 2, where is that? Is like negative I, right? This in fact is negative I. This is also negative I. If you subtract, you get 0, right? So you get 0. You see, because the exponential function has a period of 2 pi I. So z over 2 has a period of 4 pi I. I mean, e to the z over 2, it has a period of 4 pi I, and that is exactly what it is. Different by 4 pi I, so it makes the same numbers. So they subtract to 0. Any questions? All right. This is another one. Integral from negative I to I dz over z. Let me give you the pause again. Again, the integral of 1 over z becomes ln of z, right? So
Is there an absolute value in the ln of z, or is it just ln z?
ln of z. Yeah, well, for real numbers, we have absolute value, but here for every value of z except 0, there is an ln, remember?
Yeah.
All right, we have 70% in. All right. I guess that's how much we're going to get. I'm going to end it soon. All right. So this time I didn't calculate it myself, but this time A and B are close, but I think B is the answer. Some of you said undefined. Why do you say undefined? Does anybody want to share their thoughts? Why they thought that this is undefined?
Yeah, once I integrated it and I put ln I minus ln minus I,
Uh-huh.
I used the fraction law to where it's ln I over negative I, which
Uh-huh.
came -1. Which
ln
is,
of -1 in complex numbers, that has meaning. In real numbers, it doesn't have meaning.
yeah, I only remembered the real number. I kind of went over.
It's a new realm. It's a new day.
Definitely.
Only ln of 0 is undefined. ln of every other number in complex plane is defined. All right. So let's see what we get. So ln of I minus ln of negative I. Of course, you can say ln of, that's a good way. Becomes ln of I over negative I becomes ln of -1. And remember how we did ln? We can write -1 in terms of the exponential. So becomes ln, of course, with capital L. You can write -1 as e to the I pi, right? Because this it is right here. It makes an angle pi. Remember we did that, and it has a magnitude of 1. So we can write like that. So it becomes I pi. Or you can say it is ln of I becomes what? I is here. I is e to the I pi over 2, right? And then negative I is right here. Negative I is e to the negative I pi over 2. See, it has module 1, but it has a angle of negative pi over 2. So you can write pi I over 2 minus negative pi I over 2 becomes pi I. So the answer is B. Okay. Any questions? So only 0, only ln of 0 is undefined. Ln of any non-zero number in complex plane is defined. All right, because you can write it in terms of exponential. All right. We have a second method of evaluation of an integral. This was for analytic functions in a domain where the function is analytic. But now we have a second method that is correct for every case. And that is by use of parameterization of the path. If the path of integration C is a piecewise smooth path, parameterized with parameter t as z equal to z of t, where t is between a and b, and f of z is a continuous function on C, then integral of f z dz can be written as integral from a to b on t of f of z of t. Means that for every z, we replace the parameterization of z in terms of t, so we get a function of t, and dz becomes z dot of t dt, right? And then we replace dz by z dot dt. This is basically saying z dot of t is equal to dz over dt, and then cross multiply. Dz becomes z dot of t dt. Dot means derivative with respect to time, the parameter t. All right. T doesn't have to be time, but in physics it is usually time. All right, so basically we parameterize the path and then we write the integral in terms of the parameter t that we use for parameterization. And then we have a simple integral to evaluate, right? It becomes a real integral. So the steps for doing this calculation are these. Represent the path C in form of Z of t, where t is between A and B. And then calculate the derivative of Z of t, which is Z dot t equal to dz dt. And then substitute every Z of t for every Z, Z of t for every Z in f of Z. Therefore, the real part of Z, which is x, you replace it by a function of time, and also for the imaginary part, if you have in terms of x and y. Then integrate f of z of t, the z dot of t over t from a to b. So it becomes a real integral. All right. This is a example, which is a basic result that's very important. Integral of 1 over z around a unit circle. So we have this unit circle, remember, is the circle that is centered at the origin and has a radius 1. We want to take this path of integration to be a unit circle, and we want to integrate 1 over z around this circle. So remember, we can parameterize this by any point on this can be written as 1 times the x is cosine of the angle theta, and y is sine of the theta. So we write any point on this as z of t equal to cosine of t plus I sine t. You can use theta or t, but doesn't matter. Okay. So z of t equal to cosine of t plus I sine t on unit circle, or you can write it e to the it, right? Because that's Euler's formula. T goes from 0 to 2 pi to complete the circle. Then we differentiate the z. You see, this z is e to the it. If you differentiate it, it becomes I e to the it. So z dot of t becomes I e to the it. Therefore, 1 over z also, it becomes e to the negative it. The inverse of this function is e to the negative it. And then we have now 1 over z and z dot, and then we can calculate the integral of 1 over z times z dot dt. So dz over z becomes 1 over z dz dt times dt. You see, this is basically like shows the proof also. And t goes from 0 to 2 pi. All right, 1 over z is this, and z dot dz dt is this. We put those in, e to the negative it, I e to the it dt. And you see that e to the negative it and e to the it becomes 1. So becomes I comes out, it's constant. Integral dt from 0 to 2 pi gives you a 2 pi. So it becomes 2 pi I. All right. So integral of dz over z over unit circle becomes 2 pi I. All right. This is around the unit circle. This is a very important result, as I mentioned, that we will need often later. All right. It's a very good example, important example. So also an example that shows how to parameterize the curve, which was this, and then how to write the integral in terms of t, and then you do a simple integration over t, right? Any questions? All right. Integral of z to the m around any circle. So in fact, this is integral of z minus z naught over m. It's more general. Means that around any circle that's centered at z naught. So if you have a complex plane, there's a z naught, and you want to integrate this z minus z naught to the power m around a circle centered at z naught and has a radius r. How do we do that? First, we want to parameterize this circle. this is this path of integration C. We can start from here again, go around and like that, and parameterize again. We can take this angle to be T, and then this Z will be Z naught plus R cosine T plus R sine T times I, right? So this is the imaginary part. This is the real part of this Z here, delta Z. So if you write Z like this, and you can say Z minus Z naught is equal to R cosine T plus I sine T. So you can write it as R e to the IT, right? Z minus Z naught, all right? So Z of T is Z naught times R cosine T plus I R sine T. So you can write it as Z naught plus R e to the IT, and T goes from 0 to 2 pi. Z minus Z naught is R e to the IT, and Z minus Z naught to the power M becomes this to the power M, so becomes R to the M e to the I M T, right? And now we want to integrate that. So Z dot is the derivative of this Z becomes IR e to the IT, or this doesn't matter, because derivative of Z naught is 0 because it's a constant. All right, so this is Z dot. So how do we do the integral? We say integral of dz over Z minus Z naught to the power M dz. That becomes integral of Z of T minus Z naught. Z of T minus Z naught becomes e to the R, becomes R e to the IT, sorry, R e to the IT, T. This is Z minus Z naught to the power M, right? But we have this here, you could write that. And then Z dot, IR e to the IT also, then dt. T goes from 0 to 2 pi, right? So it becomes R to the power M plus 1 comes out, and I comes out. And then you have e to the power IMT plus e to the power IT, e to the power IMT plus IT dt. Or you can write I R to the M plus 1 integral of e to the power I M plus 1 t. Oh, my writing arrangement is bad. Sorry, so it becomes e to the with the constant in front, I R to the M plus 1 e to the I M plus 1 t dt. And e to the I M plus 1 t becomes cosine of M plus 1 t plus I sine e to M plus 1 t, right? And then depending on what value M has, this might be 0, might be not 0. So let's do it this way. So Z minus Z naught to the power M dz becomes this, R to the M e to the I M t times I R e to the I t. So I R to the M plus 1 comes out, e to the I M plus 1 t dt. And then we can write this as cosine of M plus 1 t sine M plus 1 t. So from Euler's formula. And then the integral breaks into two pieces. One is integral from 0 to 2 pi, cosine of M plus 1 t dt. And the other one is sine of M plus 1 t dt. All right. So if M is equal to -1, then this argument of cosine is 0, argument of sign is also 0. Of course, it has this should be also having a square bracket here. This t is also inside the argument. All right. So if m is equal to -1, then we have this is equal to r to the 0, which is 1, integral of where is the I? I think there's I here. The I is missing. Yeah. All right. So if m is -1, so we have r to the power 0 here, and cosine of 0 is 1, and we get 0 to 2 pi dt plus I r to the m plus 1, and then m plus 1 again becomes 0. Integral of sine of 0 becomes 0 dt. So that becomes 0. Then the integral of dt from 0 to 2 pi becomes 2 pi. And we had an I here, so it becomes 2 pi I. Right? So if m is -1, the integral becomes 2 pi I. What happens if m is not equal to -1? Then there is a cosine of some nt and sine of nt, and integral over the period 2 pi gives you 0 for both integrals. So if m is not equal to -1, the integral of z minus z naught to the power m dz becomes 0, because both of the integrals become 0, because cosine of nt is periodic with the period less than 2 pi, or a fraction of 2 pi. So if you integrate over 2 pi, you get 0, and also for this one. All right. So depending on what value m has, you get either 2 pi I or 0. Most of the time, for infinitely many values of m is 0. For only one value of m, it is non-zero, which is very important again. So if m is -1, we have 1 cosine of 1, and sine is, we get 2 pi I. For all other integer m, we get 0, because we are integrating over 2 pi, which is the period of the function sine of m plus 1t and cosine of m plus 1t. All right. So we have this important result. Integral of z minus z naught to the power m dz over a circle centered at z naught with the radius r, doesn't matter what radius. It becomes 2 pi I if m is -1, or 0 if it is m is not -1, any integer. All right. Any questions? All right.
Professor, one question.
Yes.
You were saying that one I was missing in the integral, in the past integral.
Yeah, but sorry,
Yeah, you said that one I was missing. I
Yeah.
just got a little confused on that part.
yeah, the I was here. See, there's an I here. I forgot to put it here. This becomes I, this becomes -1. It becomes I squared.
Oh, I see, I see.
Yeah, then remember this becomes 2 pi, and then there's I here, so it becomes 2 pi I.
Right. Thank you,
So
Professor.
the final result is the same, but I think there was I missing in the way.
Okay, I got it.
All right. So we have this result, and now there are some cases, you see, every time we have an integral that is, path independent, but this is an example the integral is path dependent, especially if the function is not analytic. Remember that fz equal to real of z is not analytic, because it doesn't satisfy Cauchy-Riemann equations. So this only has x real part. It is not analytic. So we want to calculate this integral of f z dz from the origin to this point through the two different paths, one going directly from here to there and one going along this path, C1 and C2. All right. So if you want to go along the path C star, then we can parameterize that. How do we parameterize that? We can say C star parameterization on C star. We can have Z is equal to Z of parameter T is equal to what? We need to write a function of T that gives us points along this line. Means you see this goes from 0 to 0 and 0 to 1 and 2. So it means that the y component should be twice the x component and change from 0 to 1. So can anybody tell?
T plus 2ti.
That's right, very good. T plus 2ti is the parameterization. And then we need to calculate z dot, means derivative of dz dt. That's what? It's 1 plus 2i, right? And then t goes, when we write this, we should say t goes from 0 to 1, right? If you make t go from 0 to 1, the point goes from here to here. When t is 1, say you get 1 plus 2i. When t is 0, you get 0, right? So so we write when f of z is what? F of z in this case is real of z. What is real of z in terms of t? This is the imaginary part, this is the real part. That's t, right? All right, and then so we can say integral of f z dz over c star becomes the integral t from 0 to 1, right? T from 0 to 1, and then f of z in terms of t, f of z in terms of t is just t, and z dot, which is this 1 plus 2i, and dz dt from 0 to 1. So 1 plus 2i can come out, 1 plus 2i, integral of t dt becomes 1/2 t, right? And then evaluate between 0 and 1.
Oh,
So
1/2 t squared.
T squared, yes. 1/2 t squared from 0 to 1. And then if you evaluate it at 1, you get 1/2. If you evaluate it at 0, you get 0. So you get a 1/2. So it becomes 1/2 times 1 plus 2i becomes 1/2 plus I. All right, so this is the integral over c star. Now we can integrate over c1 and c2 and add them together. If you want to parameterize this part, you can say z equal to what? It doesn't have an imaginary part, it has only real part, z of t. Z of t becomes just t, right? Because and t goes from 0 to 1. T. So this is the parameterization of C1. And parameterization of C2, you can say z of t. I want to write a function that of t that starts from here, goes up along this line.
2ti.
Sorry?
2ti, right?
2ti, but if you do 2ti, it will be here, right?
1 plus 2ti.
1 plus 2ti, yes. Very good. 1 plus 2 ti, and t goes from 0. Again, t goes from 0 to 1, right? So in both cases, but this is not unique. You could say 1 plus ti, and then t goes from 0 to 2, right? It doesn't matter. The parameterization is not unique. You can do many different ways, okay? All right. Now, if I do here, what is dz? What is z dot on C2? Becomes 2i, right? What is the dot here? The derivative of that with respect to t is 1, right? So here we get 2i, here we get 1. So in integral fz dz along this curve C that is composed of C1 and C2 becomes integral over C1 fz dz plus integral over C2 fz dz, right? And now for each one, we can write f of z. What is f of z in this case? F is the real of z. Here, all we have is real. So f of z in this case is t, right? F of z in this case is 1, right? So for this C1, f of z is t. So integral of t, then z dot, which is 1, and then dt, t from 0 to 1, plus the other one, we have f of z equal to 1 times z dot, which is 2i times dt, right? From 0 to 1. And then this becomes, this is t dt from 0 to 1. So it becomes 1/2 t squared from 0 to 1 for the first one, plus everything is constant. 1 times 2i comes out, integral of 0 to 1 of dt, right? So it becomes 2i, z dot is 2i, fz is 1. It comes out to the right amount. That's 1/2 plus 2i. Oh, yes, 2i. Right? So you see here, we get 1/2 plus 2i. Here we get 1/2 plus i. Along the C star, we get 1 plus i. Along this path C1 and C2, we get 1/2 plus 2i. So these are not the same. So the integral of non-analytic function, at least, is path dependent. Depends on which path you take from A to B. This is let's say from Z1 to Z2, or from A to B, right? So it depends on the path. All right. Any questions?
Yes, Professor. The second part
Yeah.
is from C1 to C1 plus 2i.
You see the
The second path. Can you mark it or read the second path?
Yeah, the second
Okay,
path
I
means
see.
going here and then going up.
Right, I got it, Professor. Thanks.
Yeah. All right. So this is from the book. The C star can be written as t plus 2it. It's a repetition. Z dot is 1 plus 2i. F of z becomes a t, and this becomes t times 1 plus 2i dt becomes 1/2 1 plus 2i, which is 1 plus I, 1/2 plus I. In the other two paths for C1, Z of t becomes t, Z dot becomes 1, F of Z becomes t, and t goes from 0 to 1. For C2, Z of t is 1 plus it, Z dot becomes I, and F of Z of t becomes X of Z of t, or X of t equal to 1. Here t goes from 0 to 2. You see, I did a little bit differently. I put a 2 here by recommendation of one of you, and then t goes from 0 to 1. It doesn't matter which way. As I said, it's not unique. So integral real of z dz becomes integral over c1 plus integral over c2. So for the first one becomes f of z times z dot times dt, and for the other one becomes 1 times I dt from 0 to 2. So then you get 1/2 plus 2I, and you see that these are not the same. All right? These two are not the same. So you see that it is also good that you see that it is the parameterization is not unique. I did it differently, but it doesn't affect the integral at the end. All right? Any questions? All right. I guess let's take a break, and then we do Cauchy's integral theorem. Take a 5-minute break. What time is it now? It is 12:03. We will be back at 12:08. All right. So what is Cauchy's integral theorem? In order to express the Cauchy's integral theorem, we need some definition. It is about a simple closed path. A simple closed path is a closed path that does not intersect or touch itself as shown in the figure. For example, this one are simple paths. So they don't intersect with themselves, and they don't get tangent to themselves like this. So this is not a simple path. This is not a simple path, but these are. And a circle is a simple path. A curve like an H like this is not a simple path. All right. So this is a simple closed path like this or this. And then we talk also about simply connected domain. That is a domain that every simple closed path in D in that domain encloses only points of D. So a simply connected domain D in complex plane is a domain such that every simple closed path in D means that the points of the path are in D only have enclosed only points of D. For example, here, this is a simply connected because every closed path that you take here, inside of that path are only points of this one. And this is true for this one too, but this is not true for this. For example, you can take a simple closed path here. This is a simple closed path. It includes some points that are not in D. Or you can take this point, this simple closed path. It includes some points that are not in D. All right. But in here, no matter how you draw a simple closed path, it only includes the points that are in the domain. And the same for here. You can do that like this, right? You cannot have a simple closed path that is entirely in the domain, but includes some points that are outside the domain, right? So these first two are simply connected, and the other two are not simply connected. And in fact, they call doubly connected or triply connected. How? Why they call it like that? I think from here to here, you can go from here to here. That, you know, you make a pad that has two, that has some holes in it, and in here you can, to here you can go in three different ways maybe. See, that's triply connected. This one, the other ones are simply connected. I don't know where this exactly comes from, but anyway, it's your imagination. All right. The interior of a circle, open disk, ellipse, or any simple closed curve is simply connected. A domain that is not simply connected is called multiply connected. Examples are an annulus. You know, annulus is a thing like this, is annulus. When there are two concentric circles, here's one circle and the other circle, a concentric. This is called an annulus. A disk without the center, the middle one can shrink to one point, still is not simply connected. All right. For example, this is the unit disk, but the zero is removed from it. It's not equal to zero. You see, when you remove even 1 point, it is not simply connected anymore. All right, because if you have the disk that doesn't have the center, you can have a simple connected curve in there that has 1 point that is not in the domain. All right. So these are examples of multiply connected sets or domains. A bounded domain, D, is a domain that lies entirely in some circle about the origin. So when we say bounded, it means that it has a limit. It doesn't go to infinity. All right. A bounded domain D is called p-fold connected if its boundary consists of p closed connected sets without common points. And actually, that is why I forgot that. This has two. It has two boundaries. That's why it's called doubly connected set. And this one has three boundaries. See, it's 1, 2, 3. So a bounded domain D is called p-fold connected if its boundary consists of p closed connected set. These are all closed sets because they include their limiting points, remember, without common points. So these don't intersect with each other. These sets can be curves, segments, or single points. For example, if you have a domain and you just remove a piece, line segment from it, it is not a simple, simply connected anymore. And if you remove a point here as well, it is now triply connected. If you remove something here as well, it is fourfold connected, or quadruply connected, I think they call it. All right. So these can be a point or can be just a line segment. It doesn't have to be an area. All right. As I said, for the unit circle that only origin is removed from it, unit list that only this 0 is removed from it, is also a simply connected, doubly connected region, all right, or domain. D has p-1 holes, where hole may also mean a segment or even a single point. So when we say p-fold connected, means that D has p-1 or holes in it. All right. Simply connected doesn't have any holes. If you have one hole, we call it doubly connected. Two holes as triply connected, and so forth. All right. So these are some definitions, that topological definitions that we are going to use, and you will see why they are important later on. All right. Now, Cauchy's integral theorem. It says if f of z is analytic in a simply connected domain D. You see, simply connected. It has to be simply connected. These are very important. If f of z is analytic in a simply connected domain D, then for every simple closed path C in D, we have integral of f z dz equal to 0. This is the situation. We have a simply connected domain D, and we have a path C that is entirely in that domain. If the function is analytic in that domain, then integral of f z dz is equal to 0. This is a very strong argument. It's no matter what function you have, if it is analytic over a closed path, simple closed path, the integral is 0. That's very, very strong. So some examples of entire functions. Entire functions are the functions that are analytic everywhere in the complex plane. For example, e to the z. Remember, e to the z is analytic everywhere in complex plane. Therefore, around any closed path C, e to the z dz, integral of e to the z dz is equal to 0. No matter what. Any closed path. That's very, very strong. Again, cosine of z, this is defined in terms of the exponential function, remember. Also is entire function. It is defined and analytic everywhere. The integral of cosine of z dz over any closed path is 0. Also, the z to the n for any n value, 0 to infinity. The integral over closed path is 0, right? For any closed path. These functions are entire and mean analytic for all z values, right? So this narrows it down, actually. We see it narrows down to integrals over closed paths, no matter what, become 0. There's some functions that are analytic everywhere. All right. Any questions? All right. So here is an example that shows points outside the contour where fx is not analytic, doesn't matter. For example, here, integral of secant of z dz. You know that secant is 1 over cosine, and cosine has zeros on the x-axis, plus minus pi over 2, plus minus 3 pi over 2, and so forth. Means that if you have an x, this is x-axis, let's say this is y-axis, at plus minus pi over 2 here, the cosine becomes, this is pi over 2, which is 1.57, right? And negative 1.57. At these points, cosine is 0, so therefore secant is not analytic, but everywhere else is analytic. And there's another point here, 3 pi over 2, negative 3 pi over 2, and so forth. But if you integrate over a unit circle is this. All these non-analytic points are outside. For that, you can say, okay, there is a region here, there's a domain here in which the secant of z is analytic, and we take this path, which is simple closed path, inside that domain. So this is the D. This is the simple closed path. In D. So call it C. The integral over that, according to Cauchy's theorem, is 0. Even though there is some points that secant of z is not analytic, but those points are all outside the domain, outside the circle, right? So this is very important. Secant of z is 1 over cosine z, is not analytic at z equal to plus minus pi over 2, plus minus 3 pi over 2, and so forth. But all these points lie outside C, none lies on C or inside C. And for this one, the function under the integrand is 1 over 1 under the integral sign, 1 over z squared plus 4. You can write z squared plus 4 as z minus 2i and z plus 2i. All right. Therefore, this is 0 at z equal to plus 2i and negative 2i. All right. So this function is not analytic when z is equal to plus or minus 2i. But z equal to plus minus 2i are outside the unit circle. So we're having the unit circle here, but these points are here. Doesn't matter. Again, we have a domain where the function is analytic, and we have a path inside the domain. This is D, and this is C. Cauchy's integral theorem is valid. We can say that the integral is 0. Make sense? Any questions? So you don't have to have the function analytic everywhere. You just need to have the function analytic in a domain and in the inside the on or inside, sorry, on or and inside the path of integration. If the function is analytic there, then the integral is 0. Okay? Any questions? All right. But it doesn't say anything about non-analytic functions. For example, integral of z bar dz. Z bar, remember, is non-analytic everywhere. We showed that. And if you take the integral over the unit circle, becomes z bar is e to the negative it, then dz becomes I e to the it dt. From 0 to 2 pi becomes 2 pi I. C is unit circle. All right. So that doesn't contradict the Cauchy's integral theorem because it talks about the analytic functions. Okay. The not is not analytic, so it doesn't really matter. And there are some other things that analyticity is sufficient but not necessary. What is the difference between sufficient and necessary? So it means that if you're analytic, if the function is analytic, f of z, analytic, you can conclude that integral of f z dz over closed path C is equal to 0. It does say that, but it doesn't say the other way around. It doesn't say this. It doesn't say that if the integral is 0, the function is analytic. All right? That means that it is sufficient, but not necessary. It is sufficient, this f of z analytic is sufficient for the integral being 0, but it is not necessary for integral being 0. For example, integral dz over z squared, we showed that it is 0, even though 1 over z squared is not analytic in this unit circle. So that shows that, you know, the integral can be 0, but the function is not analytic everywhere inside. This result does not follow the Cauchy's theorem because 1 over z squared is not analytic at z equals 0. The condition that f is analytic in D is sufficient rather than necessary, as I explained. Another example shows that the simple connectedness is essential. Means that, you remember the Cauchy's theorem said for any simply connected domain D, doesn't say any domain D. It has to be simply connected. Again, integral of dz over z is 2 pi I over this unit circle, right? We calculated that, but this unit circle is in a domain that is not simply connected. We can say that there is a this is the unit circle, path of integration. You can take an annulus, it's from here to here. This is not simply connected. Then the C is inside that, but it's a domain D. It is not simply connected. And you see that the integral doesn't become 0. So simple connectedness is important. Okay. So C unit circle lies in the annulus of absolute value of z between 1/2 and 3/2, where 1 over z is analytic. You see, over this domain, 1 over z is analytic, but this domain is not simply connected. And the integral doesn't become 0. So simply connectedness is important. And because the domain is not simply connected, we cannot apply Cauchy's theorem. All right. Any questions? All right. Oops. All right. Now we can also have path independence. We said that if f of z is analytic in a simply connected domain, means that we have a domain here. F of z is analytic in that, and it is simply connected domain. Then the integral of f z dz is independent of path in D. Means that if you go from z1 to z2 here, you can go this way or you can go this way, it doesn't matter. Why is that? Because instead of going you can take the integral from here going to z2 this way and come back. So you can say integral of over because it's in this simply connected domain, the function is analytic. The integral over closed path is equal to 0 of fx dx, fz dz is equal to 0. And then you can write that as integral. This is over C, which is the closed path. You can write that as integral over C1 fz dz and plus over C2 star plus integral over C2 star, which is going from Z2 to Z1 fz dz equal to 0, right? But going from Z2 to Z1 along C2 star is the same as this negative of going from Z1 to Z2 from along C2 in this along this path. So it's time reversal. We can put a negative sign here. So we say integral over C1 fz dz minus integral over C2 fz dz equal to 0. Therefore, the two integrals should be the same. So it means that the integral of fz dz is path independent from z1 to z2. All right. So this Cauchy's theorem allows us to prove that for any analytic function in a domain, the path integral, the line integral from Z1 to Z2 doesn't depend on the path as long as the paths are in the domain. And if you have a situation like this, that the path cross each other, it doesn't matter. You can write it as three pieces. One is this piece, one is this piece, and one is this piece, one is this piece. You can see that all of the around any closed path is 0. So you can say this is 0. So this part is the same as this part. And then this part is the same as this part, and so forth. So you can see that it is path independent again. All right, doesn't matter if the paths cross each other. All right. So, and then we have also the principle of deformation of path, because the path doesn't matter. You can change the path as long as you are within the domain. So you can move the path from here to here to here to here, and all the integrals will be the same. So as long as you don't go out of the domain of analyticity of the function fz, you can change the path for integral. All right. All right, so remember we calculated this integral for a circle. So for if you have this complex plane x and y, and this is z0, we said that this integral is integral of z minus z0 to power m dz is 2 pi I. If m is -1, if 0, if is 0 if m is not -1. So that was for only on a circle centered at Z0. But now we have path deformation principle. So we can say along any path that encloses Z1, Z0, we have this. All right. So this is true for any counterclockwise integration around any simple closed path containing Z0 in its interior. All right. This is very important. Now, we were limited to just this point being at the center of the circle, but now we know that it doesn't matter where it is, and it doesn't matter what shape the path of integration is, as long as it's a simple closed path, and it isn't the Z0 is inside. All right, of course, if Z0 is outside, then it is analytic. Now we can say it is 0, even if m is equal to -1. All right, any questions? So you see, we are developing more understanding of what we have here, how we deal with the integrals. And then this is just the thing that we mentioned at the beginning, the existence of indefinite integral, or the fundamental theorem of calculus. So that if the function fz is analytic in a simply connected domain D, then there exists an indefinite integral f of z of lowercase f of z in domain D, so that f prime of z is equal to f of z, which is analytic in D, and for all paths in D joining any 2 points Z0 and Z1 in D, the integral of fz from Z0 to Z1 can be evaluated using this formula in fundamental theorem of calculus. From Z0 to Z1 of fz dz becomes f evaluated at Z1 minus f evaluated at Z0. All right, for any path. All right. That was for 14.2. Now we're talking about Cauchy's integral formula, which is this very important formula. It says that integral of fz dz over z minus z0 over a closed path C that is in the domain D, where the f of z is analytic, and C contains the z naught. See, assume f of z is analytic in a simply connected domain D. Then for any point z naught in D and any simple closed path C in D that encloses z naught, we have the integral over the closed path C of fz divided by z minus z naught dz is equal to 2 pi I times f evaluated at z naught, f of z naught, right? This is very huge because we can use this to calculate integrals. All right. So if there is some denominator, we know that, okay, the integral, if the numerator is analytic and we have just one denominator z minus z naught, and the curve path of integration includes this z naught. If it doesn't include z naught, then the entire function here is analytic. The integral will be 0. But if it includes this z naught, where this integrand is not analytic within that path, then we can calculate the integral to be 2 pi I f of z naught. That gives us a huge, big tool, powerful tool to calculate the integrals. All right. Now let's do this, use it to find this. We want to calculate the integral of e to the z divided by z minus 2 around any point that includes 2. Means 2 is here, right? 2. This is 1, 2. This is the naught. Any closed path that includes 2, if you take as path of integration C, then we can calculate this integral around that C. And we can calculate it as this. This is the function that is analytic everywhere. So therefore, it is analytic in a domain that includes C. But there is z minus 2. Of course, this whole integrand is not analytic at z equal to 2, right? And then the integral, according to Cauchy's formula, let's go back to see, this is f of z. F of z is e to the z. Z naught is 2. The integral, if z naught is inside the path of integration, becomes 2 pi I times this function evaluated at this value. Does that make sense? So this function now e to the z, and this z naught is 2. So means this becomes 2 pi I, then e to the z evaluated as z equal to 2. So it becomes 2 e to e squared pi I, right? So, or 2 pi I e squared. The value of that is 46.4268 I. It becomes an imaginary number, right? So this is for any contour enclosing z naught, that is 2, since e to the z is entire and it's analytic everywhere. And 0 for any contour for which z naught is outside of it. 2 is outside of it. Right? That comes from directly from Cauchy's integral theorem, because for those paths, this whole thing is analytic in the region. So example 2, what is integral of z cubed minus 6 over 2z minus 1 minus I? How do we do this? What do you think the answer is?
I think we take out 1/2, then this would be 2 pi I g. Okay.
You said 2 pi I.
Okay. That not in I over 2. So it's I
Yeah.
2 q.
What you said the pole is I over 2, right? We should evaluate at I z equal to I over 2. So what do we evaluate?
That gq minus 6.
All right, that's the thing. See, you have to have in the denominator, you have to have z minus z naught. All right.
Yeah, I took 1/2 outside.
So, oh, okay, you put the 1/2 outside like this.
Yep. So
All right.
that's why I have the z naught equal I over 2.
Okay, all right. So z becomes z cubed minus 6 evaluated at that is correct, because now you in fact wrote the integral as you take 1/2 outside, and then you have z cubed minus 6 divided by z minus I over 2 dz. Yes, you see, you have to have here z minus z naught, not 2z minus z naught. Okay, so if you have a factor here, you have to take it out, and this changes. Now it is correct. So it becomes pi I times this z cubed. What is I over 2 cubed? Minus
Negative I over 8.
Yes. I cubed becomes negative I, and 1/2 becomes 8. So pi times negative I over 8 minus 6. Pi I. And then this becomes 6 pi I and plus pi over 8. Right? So we have to take the 1/2 outside, or you can take it to the numerator. It doesn't matter. It becomes 1/2 z cubed minus 3. And then becomes 2 pi I times 1/2 z cubed minus 3 evaluated as z equal to I over 2. And then you replace that, you get pi over 8 minus 6 pi I. All right. So you see, we're applying that formula. Z naught equals 1/2 I is inside the unit circle. Sorry, is inside the path of integration. Of course, it has to be. If it is not inside, then the integral will be 0. It doesn't specify here. So now we have an example that we want to get integral of g of z, which is z squared plus 1 divided by z squared minus 1 over around counterclockwise around each one of the 4 circles in the figure. You have circle A, this one, circle B, which is this one, circle C and D. So can you tell me what is the integral around circle D?
0, because no hole over there.
Yeah, there's no a singularity, or there's no 0 of the denominator inside that. So means that you can take a domain here, avoiding those points. This is a domain over which the function g of z is analytic, right? Because it has not analytic points here. It's outside this domain. And C is entirely inside the domain, right? So according to Cauchy's formula, the integral of g of z dz over CD is equal to 0. So that's easy. So what is the integral around circle A? And B and C. You can think about that until next time. We're almost out of time. Yes. We're out of time. So I stop here. We take it from here next time. Okay. If you have any questions, please let me know. And don't forget to do the quiz. It is due tomorrow. All right.
Thank you, Professor.
You're
See you.
welcome.
Thank you.
Professor.
Thank
You're
you,
welcome.
Professor.
Have a good day. Have a good weekend. Happy Halloween and everything.
Thank you.
You
Thank
as
you.
well.
Don't eat too much turkey.
No.
Can you upload the slides for chapter 14?
I will.
Alrighty, thank you,
This
Professor.
afternoon. You're welcome.
All right, have a nice day.
You too.
Is it possible at all to get, are you going to release any solutions for the midterm?
Release solutions. That's, I'm afraid if I do that, it will be transferred to next semester for the students. Of course, it's okay, but I can show you solutions if you want.
Well, I just wanted to know where I went wrong. So I mean, you know.
Yeah.
But I mean, you don't have to release them then. I tried to come to your office hours one day, but no one was there, so.
When?